Okay, in this video, we are going to talk about how we can build a heap from scratch. Okay, well, and we assume that we want to have, if we have an unsorted list and we just put them into an array, and then we want to massage all the data to make it a valid heap. And this is the process of the build heap operation. Okay, and as you may assume, we have a lot of heapify to do. And for each of the heapy, do we have to use the heapify to touch all the values in the unsorted array? And the answer is no. If we are considering the heap to be the subheaps, and then inside the subheaps there are also even smaller heaps, and then you will find one thing. For all the leaves, if you consider a leaf as a subheap, is that subheap already valid? Well, the answer is if there's only one value and no left child, there's no right child, and then yes, it is already the only value in that subheap is already the largest value. So what does that mean? This means if we have all the values in the list and then the right half of the list, there's no point for us to do the heapify. Why? Because that subheap, because it is a leaf, that is already a valid subheap. So we don't have to touch them. So what does that mean? When we are building a heap, we only have to touch the first half of the value, and that should be enough. Okay, so let's see the code. And well, we are touching the values from the middle index down to 1. Okay, and what does the middle index mean? The middle index will give you the first non-leaf node in the heap. And then what do? We want to do a max heap of that value, and then we move to the left side, we go all the way up to the root. We only touch the first half of the nodes in the array, and then we are done. We will be able to build a heap. So let's see this one. Well, this is just a list of the values, and if we put them in the heap structure or in the binary tree structure, and you will see, nah, this is not a heap. So how do we make them a heap? We want to touch all the non-leaf nodes, okay, from the middle value to the very beginning. So what is the first node we want to touch, or what is the first node we want to heapify? The answer is no, we don't want to touch 7, we don't want to touch 8, we don't want to touch 10, we don't want to touch 9, but 16. 16 is the first non-leaf node, so we want to touch that. Okay, so let me show you how to do that. I have already copied that to the drawing board, and then we say, we say the 16 is the first value we want to touch, but is the 16 at the right place? If we want to heapify, we only shift the value down. But for 16, is there any need for us to shift it down? The answer is no, because 16 is already larger than 7. So we are good. So 16, we are good. And then how about 2? Oh, for 2, we do have trouble, right? Because for the 2, it is smaller than 14 and 18. So what we are going to do is we want to put the 2 down. So let me shift it to the right place. So 2 should be here, and then 14 should be here. So we have already touched this node, and then we move on. How about 3? Is the 3 a node at the right place? No way, because 10 is the largest among the 3. So I want to put 10 here, and then I want to put 3 here. Okay, and then I have finished touching this node. And after that, how about 1? Oh, for the 1, that's another big trouble, because 1 should be swapped with 16. So, okay, 16 goes here, and 1 goes down here. And is this node correct? The answer is no, because it should be shifted down even further. So 1 should go down, and it should swap with 7. So 7 and 1. Okay, so just now I have finished touching this node. And how about this 4? So, okay, I have to fix this 4 again. So 4 and 16, they should swap. So let me put the 16 here. And then we put the 4 here. Oh, by the way, this is really a 7. Let me write this again. Sorry for my handwriting. Okay, 7. Okay, there we go. And then after that, is this 4 at the right location? No. So I have to get rid of this 4 and then swap with the 14. So the 14 will go here. And after that, the 4 is here. Is this 4 at the right place? No. So I have to shift it down with 8. So 8 is here, and then 4 is here. Okay, so just now I have finished touching the first value in the heap. And now, do we really have a valid heap? The answer is yes. So now we do have a valid heap. Okay, so this is the process of the heapify. To do the heapify, we don't need to touch the leaves. We only need to start from the first non-leaf node, and then we go all the way up to the root. And in this process, we may have to shift the small values down and down all the way to the leaves. So even though for some of the they started here, but eventually we may have to put them in at the right place. Okay, so this is the process of build heap. Okay, so well, now we want to do some analysis of the build heap. So for each call of the heapify, we know it takes up to O log n time, right? And then how many nodes do we have to touch with the heapify? We have to touch half n of the nodes, right? So we have to do half n of the heapify. And for each of the heapify, that is a O n log n. So what does that mean? If we put them all together, we have a O n log n. We have a O n log n for the build heap. So O n log n should be the upper bound of the build heap. So is that correct? Is that a right upper bound? And the answer is yes. Well, but is that a tight enough upper bound? The answer is actually no. A tight upper bound of the build heap is On. If that is On, what does that mean? That is a linear algorithm to build a heap from an unordered, unsorted list of the values. So why? So let's see. Well, if you want to have an observation, and this is what you will find. So roughly half of the nodes, they have the height as 0. Height as 0, it means they are leaves. And 1/3 or 1/4 of the nodes, they are of the height 1. And what does height 1 mean? Height 1 means go down by 1 level and you will see a leaf. Okay, and then roughly 1/8 of the nodes, they are of height 2. And height 2 means go down twice, you will see a leaf. Okay, well, this is not clear enough. So let me put it this way. So roughly, well, in this tree structure, well, if you see all the green leaves, all the green nodes, they can be moved down by at least 1 level, right? Because they are non-leaf nodes. So there are roughly half of them can be moved down once, or no more than half of the nodes can be moved down once. Okay? The next part, no more than 1/4 of the nodes can be moved down twice. And no more than 1/8 of the nodes can be moved down for 1 extra times or 3 times. Okay? And 1/2 plus 1/4 and plus 1/8. And we can keep on doing that. And what you will see? Well, if we have a total of n nodes, and then how many total number of the shift downs we can possibly do. That is 1/2 and then plus 1/4 and plus 1/8 and plus 1/16, and then you will find all the sum of all those values will still be smaller than 1. So n multiply a value smaller than 1 will be smaller than n. What does that mean? This means there are a total of up to n number of the shift downs, or up to n of the recursive heapify to do. Okay? And for each of the heapify, that takes constant time to move down. So there will be a total of the n up to n nodes to be shift down. So the tight bound of building a heap from scratch will be n. In other words, building a heap from an unordered list is a linear algorithm. Okay, so this is the part of doing the building heap. So we have already talked about how we can do one heapify to fix one value. And then we talk about how to build a heap. On the fly of building a heap, we may have to do multiple heapifies to fix a lot of the values. And eventually, remember our goal. Our goal is we want to have a sorting algorithm. And this sorting algorithm should be, number 1, sort in place. And number 2, it should be n log n. And the next video, we are going to talk about how we can make use of the heap to do a sorting algorithm. Okay, so I will see you in the next video.